Welcome back to CS270. I wanted to talk about concurrency and concurrent programming. What is concurrency? What is concurrent programming? Well, we saw a little bit about that when we looked at the fork function. We're able to make a process duplicate itself, and then the operating system is running both copies of this process. And then by looking at the return value of fork, we can make them each do different things. So those two programs are running at those two processes are running at the same time. They're concurrent. When I say the same time, of course, if we only have a single core machine, the processor's only executing one piece of code at a time, but it's still concurrent, or the processes are still concurrent because the operating system is switching back and forth between them relatively rapidly. So concurrent computation is when you are doing things over overlapping time periods, as opposed to sequential when you're doing just one thing at a time. Well, concurrent programming is difficult. It's not something that we're really, as humans, all that good at. We're used to thinking of things sequentially, one thing after another, maybe because when we're taking actions, when we're doing things, that tends to be how we behave. Some people might be reasonably good at multitasking, but it's still more difficult than doing just one thing after another. You have to think about how all the things that are happening at the same time interact with one another, and how something you do over here might have an effect over here, even if you weren't expecting it. So because of that, concurrent programming is pretty difficult. There are lots of different kinds of problems you can have in concurrent programs. Race conditions, also known as races, are one of the big ones. This is when what happens, the outcome of your program, depends on what order things run in. As an example, let's say I decide to check whether a file exists or not, maybe using the stat function. And then if it doesn't exist, I want to create it. Now, of course, there are better ways to do that. Open, precisely because of this problem, has flags that can tell it to create the file if it doesn't already exist. But let's say we were trying to do that with that two-step process. Check that the file doesn't exist, and if it doesn't, then create it. Well, the problem is if other things are running on the system concurrently with your program, something may, in between the time you make the check and the time you try to create the file, may have created that file. And in that case, depending on how you call it open, maybe this file that already exists gets truncated, or maybe we end up writing stuff into a file that has other things in it already. Of course, we can overwrite the things that are already there, but maybe that means there's junk left over at the end after we write our file, if the new one and the old one, if the new one was shorter than the old one, for example. Of course, this isn't just a computer problem. Things like that happen in the real world. Imagine you go to the airport. I realize it's probably been a while since some of you have been to the airport, and might be a while before some of us get to go to an airport again. But let's say you're at an airport and you're ready to board a plane, but it turns out it's overbooked by one seat. So there are 200 seats on the airplane, and there are 201 people waiting to board. So what do? Well, you could pick the order in which you allow people to board, and whoever's left over last is just left out. But depending on the order, different things are going to happen. Well, what happens if that last person is traveling with a family and doesn't want to be left behind without them? So they decide, so they're not able to go. Meaning the rest of their family decides not to go, and then now there are more seats available on the airplane, so they could let them go, but then the other member of their family wouldn't want to go, and so on. There's a pretty funny example of this in an old Arlo Guthrie song, The Pause of Mrs. Claus, where he talks about being followed by the FBI. He was a singer in the 60s and a little bit radical at the time. And what happens if it's the last seat? If he gets on, then the FBI agents following him can't get on. So then he gets off, meaning they're allowed to get on, and so on. Another thing that can happen is deadlock. So this is where multiple things would be running at the same time, but they can't make any progress. Each one is waiting on the other one to do something. So, for example, if I have improperly programmed my network protocol, the client thinks that it's supposed to wait for the server to send a message. The server thinks that it's supposed to wait for the client to send the message. And, well, they're both going to sit there waiting for the other to send a message. That will never happen because the one that, whichever one should send the message, is instead waiting for the other one. And then a related issue called starvation or live lock, which is when you're able to make some progress. Some of the processes are able to run, but they're preventing one of the processes from ever getting to do anything. So all of these are problems that can and do happen frequently in concurrent programming, and the, I guess, goal of being a good concurrent programmer is to recognize these and avoid them. And there are algorithms that can be used to avoid some of these situations, or there are mathematical proofs you can make to show that this new algorithm you've invented doesn't have deadlock, for example. But it's still a tough problem. Now, we're not going to get into all the details about concurrent programming. That is an entire course, really more than one course, but that would be an entire semester or more worth of things specific to concurrent programming. But I did at least want to talk about concurrent programming a little bit to get an idea of what the issues are, to get an idea of how it's done, so that you can learn more about it in the future. And so you can see how it affects some of the systems programming that we've already done. So in particular, let's take a look at the Echo server. So this was from the chapter on network programming. There's another copy of the same Echo server in the Lecture 17 code, as well as two other versions of the Echo server. But let's take a look at the iterative version first. This is the one we looked at in the previous chapter when we were looking at network programming. So in the server, it opens a listening file descriptor, which, remember, really means creating a socket, binding that socket, calling listen on the socket, and then open listen FD also before all of that does get name info and so on to convert a string into an IP address. But in any event, once we've done all of that, we have a listening socket. All we can really do on a listening socket is accept connections. And when we call accept, that waits for a new connection to come in, returns a new file descriptor, the connected file descriptor, which allows you to read and write with the client that you just accepted a connection from. So we call accept, it blocks, it waits for a connection to come in, it returns this file descriptor. Then we call some more stuff, and eventually we call echo, this function which isn't implemented in this file, but that waits for a line to come in from the client, sends a reply back, does that in a loop until the client has closed the connection, until it reads into file. Well, the problem here, and we talked about that when we were looking at the program the first time, is that that echo function can take arbitrarily long as the client is still connected and is either continuing to provide as input or is not providing as input, in which case we're kind of deadlocked waiting for that input. But as long as it's doing that, this echo function doesn't return, meaning we're not in the middle of an accept call. We're not accepting any more connections coming in until we've handled this client that we're already handling. Now, there might be some situations where something like that is acceptable, but as you can imagine, in most network servers, that's not. Maybe it takes a few hundred milliseconds to serve a particular web page to handle reading all the files and sending them over the network and so on. But while that's happening, other people are still trying to connect. If you make everyone wait until that 100 milliseconds has elapsed, that in itself might not be too big a delay. But if 10 people trying to connect in that time, you've now got a second before you can make the last one's connection. And during that second, you might have 100 more connections, in which case you've got 10 seconds before you can go through them all, and so on. So connections might be coming in faster than any one can be handled. But that doesn't mean that that the computer doesn't support the traffic. The problem here isn't necessarily the bandwidth we have, but the latency. There's always a delay in handling network traffic. And if we just wait while that delay is happening, rather than doing other things like handling other connections, we're wasting system resources. We are having our processor spend most of its time idle when it could be doing work. So this iterative echo client or echo server is not so great. So what else can we do? So again, just as a diagrammatic version of what I just said, the client connects, the server calls accept, it reads, which is going to wait for the client to call write. Then the server will write, it will wait for the client to call read, and so on, back and forth. Eventually, the client closes, the server will read, get an end file, and close the connection itself. Echo returns, and then we can go on and accept, read, and write. But while this period of time is going on, between the server calling the echo function and the second client trying to connect, we just have to wait. All right, so it turns out actually that was a little bit of a lie. And this diagram also showed that as well. The client's connection attempt actually returns, even though the connection hasn't been accepted. And that's because on the server side, the operating system is actually accepting that connection on behalf of the client. It hasn't returned the connected file descriptor to the server yet. That won't happen until the server calls connect again. But it is at least maintaining that backlog. So the client is actually running. The problem is when it calls read to wait for the server to send something back, then it has to wait. And on much older systems, and I mean very, very old, without that backlog feature enabled, we really would be waiting for the connection to happen at all. So, and the real problem with that is, of course, the first client might forget to read something. The user is typing things in, goes out to lunch without making connection, and now that other client is waiting really indefinitely. We have a deadlock. So the solution to this is to use concurrency. Don't let the server stop running or stop accepting connections just because it's already got one connection going on. But how do we do that? Well, there are a few different options. So process-based concurrent servers, we use fork. In the server, after we accept the connection, we fork, let the child process handle that connection, and in the parent process, we go back to accepting another connection. and that's pretty handy. We'll talk about some issues about that later. We don't have to worry about it at all in our program, in that the kernel is handling that concurrency for us. We do have to worry about it because each of those processes, the child process that is handling the connection, the parent process that is waiting for new connections to come in, are independent. They have their own address space. Well, this is both good and bad. It's good because it means one client or one connection handling one client can't mess things up with another connection handling another client. On the other hand, it means that those different server processes are going to have to use um, pretty complicated methods to communicate with each other if they need to, for example, share access to a database. So the second kind, which has its own problems but eliminates some of those, is an event-based concurrent server. And in an event-based concurrent server, the programmer is handling that manually. So it turns out there's a system call called select and a related one called poll. Select is kind of the old-fashioned version. Poll or epoll is the more modern version. But this system call allows you to take a bunch of file descriptors and say, wait for something to happen on one of those and tell me which one it was. So then in our server, we can do a select on the different file descriptors belonging to the different client connections, as well as the listening file descriptor that's waiting for connections, call select on it. And so when select tells us that something's happening on one of those, somebody tried to make a connection to the listening file descriptor, or one of the clients just sent us something, or is waiting for something in the connected file descriptor, we can handle that particular file descriptor. We're using just one address space, so we can share whatever we want. Sharing, of course, means we have to be careful not to stomp on each other's data. But because the programmer does have to handle that manually, it's not that easy to do. It's fairly complex. This was a pretty common way to handle servers. Well, actually still is, but was a particularly common way to handle servers, let's say 10 years ago, before, or 15 years ago, before multi-threaded processors were common. But since we are running all in the same address space, all in one process, we can only use one processor this way. So even if it does sometimes let us be a little more efficient at the cost of more difficulty for the programmer, with multiple processor cores, it becomes even more disadvantageous. And then finally, there's thread-based. So we'll talk more about threads in a later video, but the idea is we have something that's kind of like a process, in that we have a separate thread of execution, a separate set of registers, and those registers include the instruction pointer, so I can have two things running the same code or different code, but they share the same address space, so they're all within one process. So it's kind of a hybrid of a process and something. We'll see more about that later. Let's take a look in the next video then about process-based servers and maybe event-based servers. So thanks for watching.